Section 13.3, arc length and space. So some learning goals: be able to apply arc length formula, know the definition of an arc length parameterization, and be able to compute one in appropriate situations, and be able to find unit tangent vectors. Okay, so arc length, this is something that we study a couple times back in Calculus 2. So the idea here is that you have some curve in space, and we want to find what is the total distance that you would travel. You'd walk from here to here. And if you remember the first version that we saw of this, assuming where we were thinking of this as y as a function of x, was 1 plus f prime of x squared. Take the square root of that and integrate that from a to b. And then later on, when we did parametric functions, instead of doing this, we're thinking of x of t and y of t. This is nice, we can do more interesting figures in the plane. And so this is the integral from t1 to t2 of the arc length for this one, where t1 is the initial time, t2 is the ending time, of x prime of t squared plus y prime of t squared, and integrate this with respect to t. But now we're thinking of r of t as a three-dimensional vector, x of t, y of t, and z of t. Well, guess what? The formula ends up generalizing in exactly the way you would hope from this formula. So instead of having x prime of t squared plus y prime of t squared under the square root, we get x prime of t squared plus y prime of t squared plus z prime of t squared under the square root. And so here's our formula. Here's our definition for the length of a smooth curve. R of t is x of t I hat plus y of t j hat plus z of t k hat, where t runs from a to b. That's traced out exactly once for the values of t there. Is given by L as the integral from a to b of x prime of t squared plus y prime of t squared plus z prime of t squared. It's the same formula as we had before. Maybe you've used a little bit of different letters, and then throw in one extra term here. And then also this maybe lets us onto a little dirty secret here, that back when, we're doing, this is supposed to be a new thing, chapter 13 on vector functions, really, when we were doing the parametric equations, at the tail end of Calculus 2, really we were doing vector functions in some some sense. We weren't using vector notation, but it's equivalent where our vectors would just have two components instead of three components in them. Okay, so this is our main formula for the section. I peek to see what's coming up next. Let's just observe here that the thing that's under the square root here, the first component of the velocity squared, the second component of the velocity squared, the third component of the velocity squared, take the square root of that. This is just speed. This is, the magnitude of our velocity here. And so a very succinct way to write our arc length formula is this. L is the integral from a to b of the speed, integrating the speed with respect to t. Okay, so let's do an example of this. So the glider soars upward following the path r of t is cosine t I hat plus sine t j hat plus t times k hat. Find the distance traveled for t is running between 0 and 2 pi, finding the length of the curve of this curve between 0 and 2 pi. Okay, so what do we have to do here? So v of t, we know we need the velocity here. The derivative of cosine is negative sine of t I hat plus cosine t j hat plus the derivative of t k hat is just k hat. And so now we care about the speed here. And so to find this, we take the square root of the sum of the squares here, minus sine t squared plus cosine t squared plus the component there is 1 squared. And so this just ends up as sine squared t plus cosine squared t plus 1. Sine squared t plus cosine squared t is 1, so 1 plus 1 is 2. So as it turns out here, the speed is constant. Our speed is constant here, and so this allows us to then very easily apply the arc length formula, 0 to 2 pi, and that's going to be square root 2. And this is, a very easy integration to square root 2 pi. So this is how you apply the arc length formula. This is an example in which the integration was very, very easy. Sometimes the integration here will require a little trick that you'll have to do some trickery to get the the speed simplified down to something you can integrate. And sometimes it will just be impossible for you to integrate, in which case it's perfectly fine to just write down that the arc length is, integral from wherever to wherever, and, simplify the speed as best you can, even if you can't integrate that. Okay, so that's our intro to arc length and space. Let's end this video with a pre-class problem. Find the length of this curve. R of t is 2ti hat plus t minus 3j hat plus 6t plus 1k hat, where t runs from 1 to 8.